Welcome back in the third lecture of this course. In the previous lecture, we learned about the different energy sources and the energy carriers for transporting energy. But how do we transport energy to our houses? In this lecture, you will learn about this and what we need to transport energy. The learning objectives for today are first to explain the need for transport and conversion in the energy chain. And secondly, we are going to reflect on what energy conversion entails and where it occurs in the energy chain. Here is an example of the electricity grid. On the right, there are houses in need of electricity. There are two sources of electricity. The far-away production is represented by a power plant and a wind farm. But also nearby production is possible in the form of rooftop solar panels. These panels convert solar energy into electricity, which can then be consumed locally. For the solar production, transportation is not required, since it is locally produced. But the amount of generated electricity is typically limited. The alternative is the far-away production in large-scale power plants or wind parks. For that, we need long-distance transport. This transport is facilitated by the overhead lines and the underground cables of the electricity grid. We use electricity in our houses for different applications. For instance, during wintertime, we can use electricity to heat our houses. For this, we need to convert electricity into heat. Energy conversion is, by definition, the process of changing energy from one form into another. By energy conversion, we change the energy carrier. Electricity can be changed into heat, but we can also change coal into electricity. In this conversion process, we obtain useful energy, but some part of the energy is lost. We know that energy cannot be destroyed, so this energy loss is actually not useful energy. An example is the waste heat when we burn coal to generate electricity. In this slide, different examples of energy conversion are given for the three main energy uses: heating for buildings, electricity for different applications, and mobility for commuting. Starting from an energy source, we convert energy through a single step or through multiple steps. A single-step conversion is, for instance, converting gas for heating in our houses, or solar energy into electricity. For some other uses, conversion is performed through several steps. As an example, for mobility, the primary source is crude. We convert this crude to gasoline through refineries, and the engine of a car then burns gasoline to generate heat. This heat propels the pistons inside the engine, which eventually turn it into a mechanical movement. When we have one energy carrier and we convert it to another form, there are losses by definition. The efficiency is a measure for the amount of energy lost in the transformation process. To be more precise, the energy conversion efficiency is the ratio between the useful energy output to the total input of energy. The useful output energy equals the input energy minus the energy losses. As an example, the typical conversion efficiencies are indicated between chemical energy and electricity. First, for the conversion of chemical energy, for instance in the form of fossil fuel, to heat, the efficiency is up to 90%. The efficiency of the conversion from heat to mechanical energy is something like 60%, depending on the device. And the efficiency of the conversion of mechanical energy to electricity is up to 90%. Typically, energy flows and conversion are represented in a so-called Sankey diagram. A Sankey diagram visualizes the energy conversion for different purposes. This can be for a whole country, or for the world, or for a smaller system. On the left side of the diagram, we find the different types of energy sources and their magnitude. These energies then flow in different directions, and the width of the arrows is proportional to the flow rate. The end use of the energy is shown on the right side of the diagram. In this figure, we show a Sankey diagram for a simple process factory that imports fuels, steam and electricity and has its own on-site renewable electricity generation. The boxes in the middle represent the conversion steps. For instance, we can see that some fuel is converted into electricity through on-site generation and is then used with other electricity as process energy. The Sankey diagram also shows the energy losses from each conversion step. And the overall efficiency can be easily calculated from such a diagram. Finally, depending on the transportation and conversions needed for each primary source, the energy chain becomes different. For solar panels, transportation and conversion are limited and the energy chain is short. When we use wind energy to generate electricity, we convert the mechanical movement of a wind turbine into electricity, and we then transport it to our houses. For fossil fuels used for generating electricity, the energy chain is longer because we start by the conversion of crude into refined oil, and then we burn this as fuel in a furnace to generate heat through which we generate electricity. The more conversion steps we need, the higher the energy losses. Therefore, renewables have an advantage over fossil fuels because they require less conversion. However, the use of renewables has some disadvantages as well. In the next lecture, you will learn about some of them and how you may deal with it.